In this video, we're going to be looking at related rates, one of the best applications for differentiation. Now, what's the objective? Well, you're going to have to be able to find the derivative with respect to time. You're going to be given an equation, and you're going to have to take the derivative with respect to the letter t. All right? So the next objective is to solve real-world situations using the derivative. All right? Now, what are related rates? What we're trying to do is we're trying to find a rate of change of one variable with respect to other rates of change. So in other words, you might say that the area of a circle actually depends on the rate of change of the radius. All right? So we try to connect them by taking the derivative with respect to time. In other words, one variable will be depending on another variable. All right. Now, the related rates is like implicit differentiation. And I don't know if you remember when we did implicit differentiation, there's a video on it. You can always go back and look at that. Let's pretend I gave you x squared plus y squared is equal to 25. I give you a circle like this. And I say take the derivative of that with respect to x. And you would say, well, the derivative of x squared is going to be 2x. And we never ever put dx over dx because dx over dx is just 1. And then over here, I'm going to take the derivative of y squared, so the derivative of y squared is 2y, but then I took the derivative of y with respect to x, and the derivative of 25 is 0. So what we really learned is that every time we take the derivative of a y, we had to put what? We had to put dy dx. This is what we had to put. All right? So what we're going to do is we're going to look at implicit, and implicit, every time we took the derivative of y, we had to put dy dx. Now, in related rates, every time we take the derivative of any letter, including x, we have to put d variable over dt. All right? So here we go. What we're going to do is we're going to compare implicit with related rates. So if I gave you the expression x squared plus y squared, and I said take the derivative implicitly, you would say, well, the derivative of x squared is 2x, the derivative of y squared is 2y, and then of course I would put dy dx. Now, if I was taking the derivative with respect to time, the derivative of x squared would be 2x, but now I have to include the change in x over the change in time. Plus the derivative of y squared would be 2y, and I have to include the change in y over the change in time. Now, what about this one? This one here is, there's no plus between a minus or a minus between them, so I'm going to have to do the product rule. All right? So the derivative of x is 1 times y, plus the derivative of y is going to be dy dx times x. And now that right there was implicit. Now, if I was to have done related rates, I'm going to take the derivative of x now with respect to time, so that's going to give me dx dt times my y plus the derivative of my y with respect to t times my x. All right, so are you noticing something different about related rates? On this one, we're always going to put d letter over dt. Now, let's go ahead and look at one more function. We have the sine of x and the tan of y. Well, in implicit, the sine of x is just going to be cosine of x, and the derivative of tan of y is going to be secant squared of y, but then I have to include dy dx. In related rates, I'm taking the derivative of sine of x, which is cosine of x, but now I took the derivative of a letter with respect to time, so I have to put dx dt minus secant squared y, and now I have to multiply that times dy dt. So I hope you're looking at that and says, oh my gosh, I'm understanding related rates. It's not that difficult if you understand that you're always going to include d letter over dt. All right? So basically, what's the most important thing that you're supposed to understand from here? That if you take the derivative of any variable, you must then multiply it by d variable over dt. Okay? So let's do some quick derivatives here with respect to time. Well, the derivative of p is going to be dp over dt. I have to include that. Now, what's the derivative of 2l? Well, it's going to be 2dl over dt plus the derivative of 2w is 2, and then I have to multiply that times dw dt. So that means that the change in the parameter is not only going to change in the length, but it's also going to change with respect to the change in the width. All right, so that means that dB dt is dependent on dL dt and dW dt. Okay, let's try another one. This is one of the most important ones that you're ever going to see on related rates. It's probably something that most of the professors like to include on their exams. So let's take the derivative of this with respect to time, and you're going to say, well, the derivative of a squared is going to be 2a dA dt, plus the derivative of b squared is going to be 2b dB dt, and the derivative of c squared is going to be 2c dc dt. Okay? All right, let's try one more. We're going to take the derivative of this with respect to time. I'm sorry about that. The derivative of a is going to be dA dt. And here, I'm multiplying them. And remember what we said, whenever we're multiplying two variables, we have to do the product rule. So what I like to do is I like to use my notation, which I call it ABBA, right? So this will be my A bubble, and this will be my B bubble. And if you're saying, what is he talking about? Well, you can always see my product rule, or my quotient rule. Oops, that's supposed to be a B, not an R. A prime B plus B prime A. And it's ABBA because it was when I started teaching calculus, ABBA was very popular with Dancing Queen. So now, what's the derivative of my A bubble? Is going to be 1/2, and do not forget to put the dB dt, times my B bubble, which is an H, plus now the derivative of my B bubble is going to be dH dt, times my A bubble, 1/2 B. And that's it. That's going to be my derivative of A with respect to time. Okay, so that means that it's dependent on dB dt, and H, and B, and dH dt. So the change in the area depends on 4 things. Now, what's the strategy for solving real world related rate problems? All right. Usually what I recommend is to draw a picture naming the variables and the constants. All right. Read the problem, write down the numerical information that's given and what they're asking for. State the formula that relates the variables, take the derivative with respect to time, substitute and evaluate. And that's it. That's 5 easy steps. You might think that's not so easy, sir. Let's go ahead and look at 2 examples. The first one says, a girl is flying a kite at a height of 300 feet and the wind carries the height horizontally away at a rate of 25 feet per second. How fast must she let the string out when the kite is 500 feet away from her? Okay, so what we have is we have a little girl. I'm going to draw my picture up here. Okay, so let's put some long hair on that little girl. And she's flying a kite, and the kite is up here. And it says that the kite is 300 at a height of 300. So this is going to be 300 feet. That is not going to change. Okay. Now, a girl. It says a wind carries the kite horizontally. So horizontally means this way. So this right here is going to be 25 feet per second. And usually the units are very helpful for me. So this right here, he's going to be a related rate. Okay? So it's a change in distance over the change in time. So as soon as you see time on the bottom, you say, oh my gosh, that's going to be a D letter over dt. Okay? Now it says, how fast must she let go of the string? How fast must she let the string out when the kite is 500 feet away from her? So that means that this one here is going to be 500. Well, I know from geometry that, Mr. Quintana, if this is 300 and this is 500, that's a 3, 4, 5 triangle. So that means that this length here is going to be 400. Okay, so you could have done the Pythagorean theorem if you wanted to. Okay, so now what I did was I read the problem, and now what I have to do is says how fast must she let the string out? Well, in this side over here, in this part right here, there is no string involved. That's just the height. Okay, so I'm going to find a formula. Well, this is the rate that's being changed here. This is the rate that we're trying to find here. So that's going to be dc over dt. And I chose C because I'm looking at it. I'm looking at the Pythagorean theorem. So the formula that I'm going to use is going to be a squared plus b squared is going to equal to c squared. All right. So let's take the derivative of that, which we did in a previous slide. 2a dA dt plus 2 to be dB dt is going to equal to 2c dc dt. So in my picture, I can honestly say that this right here is going to be my C. This one I'm going to call it my A, and this one here I'm going to call it my B. Now remember, I found the B using the Pythagorean theorem. Okay. Now, what is this? What is a 25? The 25 is going to be classified as my dB dt and my dA dt. And here's something that you got to be very careful here. The height is always going to be 300 feet above. Isn't that? In real life, it's going to go up and down. I know that, but in this scenario, it's just going horizontally, but it's going to stay at the same height of 300 feet. So that means that dA dt is going to be 0, and dC dt says how that's going to be the change in my hypotenuse, and that's what I'm looking for. That's my question mark. So in this scenario, this is my question mark. My C is going to be 500. My A is 300, but my dA dt will be 0. And my B here, my B is going to be 400, and my dB dt is going to be 25 feet per second. So when I solve for this, 0 times anything is going to be 0. So I'm going to be left with 800 times 25. So I'm going to take a calculator. So I know I'm a math teacher, I'm supposed to do that, but I don't want to do that today. 800 times 25, that's going to be 20,000. Okay, 20,000. And on the other side, I'm going to end up with 1,000 times my dC dt. So then when I divide by 1,000, this is actually going to simplify, and I'm going to end up with 20. 20 is going to be dC dt. Now, when you're doing these problems, you have to understand that, yes, 20 is a great answer, but you also have to include my units. And in this case, we're talking about feet. So dC dt is going to be feet. And what is my length of time that I'm using in this? Well, the other one was telling me that it was 25 feet per second. So in this case, it's going to be feet per second. So the answer here, dC dt, is going to be 20 feet per second. And this is going to be my answer. Okay? So let's go ahead and look at another problem. All right? We have a sand that's being dropped from a conveyor belt. Okay? And I'm going to make it. It's coming from a conveyor belt. So here's a conveyor belt. Ooh. And sand is going and is being dropping. And what is it going to form? It's going to form a little cone here. Okay? It says conical pile. And look what it says here. It's going to be 10 cubic meters per minute. So right here, I know what this is. This, the top part is telling me meters cubed. It's going to be a volume over time. So that's going to be a dV over dt. The height, they tell me that the height is always 3/8 of the diameter. Okay, so instead of using the diameter, I am going to make a cone here. This is my diameter, but my formula that I'm going to be using has an r in it. So what I'm going to do is I'm going to convert the diameter to radius. So it's going to be 2r. So that means that h is going to be 3/4 of a r. Okay. It says, how fast is the radius changing? So in this scenario, they're telling me, right here is telling me to take the derivative with respect to time. So it's changing. The radius is changing. So they want dr dt. So dr dt is going to equal to my question mark. When the pile is 4 meters high. Ooh. I put in a t there. So it's 4 meters high. So that they're telling me that my height is going to be 4 meters. So what do I need? I need the volume of my cone. And the volume of a cone is going to be, what is it? Volume of a cone is pi r squared times the height, and it's going to be 1/3 pi r squared. Okay? Times the height. But now they want me to take the derivative with respect to time. So I'm going to get dV dt is going to equal, and I have to do the product rule. So this guy is going to be my A bubble, and this one's going to be my B bubble. So I'm going to do the product of A, which is 2/3 pi r dr dt times my H plus dH dt times 1/3 pi r squared. So when I look at this, they're telling me here, you see how I got dv dt here? I have dv dt on the left side. Well, up here, I know that this was dv dt. So that means that I'm going to substitute. For my dv dt, I'm going to substitute a 10. All right, and I'm going to have 2/3 pi. Do I have my radius? Well, I don't have my radius, but I can find my radius because they're telling me that my height is 4, so this is going to be 4. So that means that I'm going to say 4 is going to equal to 3/4 r. So when I cross multiply here, I'm going to end up with 16/3 is equal to r. So that means that my radius is going to be 16/3. Okay? I hope that's right. 4 times 4, 16, yes. And then dr dt, which I do not know, but that's what I'm looking for, right? Dr dt times the height of 4 plus dH dt. Now, here's an interesting part that a lot of people say, hey, sir, dH dt is not given to me. Well, you're going to have to use this other equation, and I'm going to have to take the derivative of that. So if I take the derivative of the second equation, I'm going to get dH dt is going to equal to 3/4 dr dt. So that means that right here for this dH dt, I'm going to put 3/4 dr dt. But sir, there's a dr dt. Well, that's what we're looking for. So that guy and that guy are going to be able to be factored out to go from 2 to 1, right? And then I'm going to multiply times what? 1/3. Let me see if I can move this cursor. There you go. And I'm going to have 1/3 pi r squared. But my radius, we said my radius was what? 16/3. So I'm going to have 16/3 squared. Okay. So this is going to be a nifty little problem to do. So I'm going to have 10 is going to equal, and right here I'm going to end up 2 times 16 is 32. 32 times 4 is going to be 128. So I'm going to have 128 pi over 3 times 3 is 9 times dr dt. Plus over here I'm going to end up 16 times 16. I believe that one's going to be, is it 256? Let me check it. Yes, 256 times 3. That's going to be 768. So I'm going to have, oops, but wait a minute. I don't have to multiply it times 3 because I know that this 3 here and this 3 are going to reduce. So 16 times 16 is 256 on top, right? And on the bottom I'm going to get 9, which is 3 squared is 9 times 4. 9 times 4 is 36 pi dr dt. Now, I have dr dt right here also. So how do I go from 2 dr dt's to 1 dr dt? Well, I'm going to factor it out. So 10 is going to equal to 128 pi over 9 plus 256 pi over, oops, that's supposed to be a 36 here. 36, and I factored out the dr dt. Now, the thing is that I can actually add these two together, right? So I can multiply by 4. I can multiply this by 4 so that they can have the same denominator. I can multiply it by 4. So 10 is going to equal to 128 times 4, that's 32, 8, 11, 4, 5, 12. I'm going to get 512 pi over 36 plus 256 pi over 36. Now they have the same denominator. So that means that I'm going to end up with 36 on the bottom, and on top I'm going to have to add those up. 8, 6, 768 pi times dr dt. Now to get dr dt by itself, what I'm going to have to do is I'm going to have to divide by this quantity. I can divide it, or it's a lot easier to just multiply by its reciprocal so that everything can reduce to a 1. So I'm going to multiply by 36 over 768 pi. So my final answer, that means that dRdt is going to be 360 over 768 pi. Now, what would be the units? The units in this problem, if you look at it, it's going to, they're talking about meters, cubic meters per minute, and it's 4 meters high. So the change in my radius is going to be meters. And what's the change in my time? We said the change in time was seconds, was it minutes? Minutes. So it's going to be meters per minute. And that is my answer. Okay? And that concludes the video on related rates.